Hi everyone, it's wonderful to see you again at Emerge. If you don't mind, I suggest you to turn on your camera and say hi to each other and share where you are if you are outside Berkeley. I'm E, PhD candidate in systems engineering at Berkeley, and I'm the organizer of Emerge Seminar. The Emerge Seminar is a weekly platform where early career researchers can present their work, refine ideas, and build community across mobility, energy, infrastructure, and sustainability. We launched this series 2 weeks ago with a phenomenal talk by Dingyi Zhuang from MIT. Many of you attended the seminar, but if you missed it, or if you would like to review the presentation again, you can now find the slides and recording at our Emerge homepage. Let me show you how to find them. So on this page, you'll find the abstract, the speaker's bio, slides, recordings, suggested readings, and also photos and more photos. And also let me highlight a few more features on our homepage. The most important one is to join our mailing list if you haven't done so yet. You'll also find our lineup of upcoming speakers with some slots remain open that we hope you'll help us fill by nominating top candidates. Finally, we update the coming next session every week with the latest seminar information. And today, we are very fortunate to welcome Dr. Xinyu Dou as our second Emerge speaker. Dr. Xinyu Dou is a postdoctoral research fellow in the Department of Earth System Science at Stanford University, supported by Stanford Energy Postdoctoral Fellowship. She received her PhD in ecology from Tsinghua University under the supervision of Professor Zhu Liu, where she developed GRACE, the world's first near real-time grid-level carbon emission database at a daily scale. Xinyu is a key member of the International Carbon Monitor Project and a contributor to the Global Carbon Project. And today, her talk title will be Near Real-Time Monitoring of Carbon Emission Amidst Global Energy Transition. And without further introduction, please join me to welcome Dr. Xinyu Dou. And Xinyu, the floor is yours. For 40 minutes presentation, will follow by a Q&A and free discussion. Thank you.
Thank you, E, for your kind introduction. Good afternoon, everyone. I'm Xinyu, a Stanford Energy Fellow. I'm very glad to be here to share my research with you. And let me share my screen. Can you see my screen?
Yep.
Okay, thank you. Okay, so I'm very excited to share my work, which focuses on near real-time monitoring of carbon emissions from human activities amidst global energy transition. As we all know, greenhouse gases are gases in our atmosphere that act like a blanket. They trap some of the heat from the sun and keep it from escaping back into space. Since the industrial era began around the year 1850, human activities have released a lot of greenhouse gases into the atmosphere. These human-made, or we call anthropogenic greenhouse gases, are the main reason our planet has already warmed by about 1.5 degrees Celsius. And among all these greenhouse gases, CO2 and methane are the two largest contributors to global warming. They are responsible for most of the warming we see today. Now, our observations show that the concentrations of both CO2 and methane in the atmosphere keep rising, as you can see from these figures. Now, even though there is more than 200 times as much CO2 in the atmosphere compared to methane, methane is a much stronger greenhouse gas. Its global warming potential is about 28 times greater than CO2. So because of this, methane contributes to about 30% of the warming we see today. And CO2 accounts for about 50%. Together, these two gases are responsible for about 80% of global warming. So that's my research focus on these two greenhouse gases. We know their concentrations in the atmosphere are increasing. But if you have such a question, the main reason for that is what? It is the increase of the emissions caused by human activities. Human activities have caused a large amount of emissions, especially after 1950, due to the large-scale fossil fuel use. So my research starts from this part of emissions, the fossil emissions. The Global Carbon Project published annual reports that reviewed all the sources of CO2 and methane emissions. And according to the latest reports, for CO2, the fossil emissions are from the consumption of fossil fuels. And for methane, the fossil emissions means the emissions from fossil fuel production and transportation. And in the face of the severe climate change, how to accurately quantify the fossil carbon emissions is very important. Only with these accurate values can we track the progress and design the effective solutions. But in the field of emission quantification, we're faced with a core scientific issue, that is, how to quantify the true value of emissions. Unlike the atmospheric concentration that can be directly measured by instruments, emissions cannot be directly measured by physical means. It requires the integration of investigation, measurement, simulation, statistics, and other aspects. And in short, there are two main methods can be used to quantify carbon emissions. One is top-down emission inversion. It means estimating emissions based on observed concentrations and the atmospheric transport models. And another method is bottom-up emission inventory model. It is a statistical calculation. It uses activity data and emission factors to quantify the emissions from specific sectors. Each method has its strengths and limitations. Let me show more details. For the top-down method, we all know that atmospheric observations can provide relatively accurate spatial distribution for gas in the atmosphere. And especially with the development of a satellite, we can monitor emissions in hotspots. Especially, we can capture some abnormal methane links. However, for CO2, the current carbon satellite observations samples are still very limited. They're limited to local areas such as power plants or big cities. So it is difficult to quantify the global CO2 emissions using top-down approach. And also there are some large uncertainties in the measuring instrument and the inversion models themselves. And another method, bottom-up, can distinguish and quantify the specific emission source. Using this inventory method, the emissions from fossil fuel use and industrial processes can be accounted with relatively low uncertainty. This is because this inventory method is based on the principle of material balance. The calculation method and parameters are relatively simple, and the energy statistics are generally collected by national statistical agencies, and the emission factors can be determined experimentally. As a result, the overall uncertainty is relatively controllable. This method has been compiled into an accounting guide by the IPCC and provided to various countries for accounting. Well, there are some limitations for this approach. That is, since the energy statistics used here are traditionally used as the activity data for the calculation. So the inventories are usually limited to the annual resolution and the lack of more than 1 year because the limitations from energy statistics. In addition, for the methane emissions accounting, this method cannot account for the emissions from abnormal events that not recorded like the ultra emitters methane links. But this part of methane linkage emissions cannot be ignored. And in the current background, there is an urgent need for near real-time carbon emissions monitoring across governments, societies, and companies. At the government level, near real-time monitoring makes it possible to quickly check how well climate policies are working in different regions. And it also allows for tracking the process toward temperature targets and some other policy targets like carbon neutrality and carbon peak and so on. Moreover, near real-time emission data can offer more timely inputs for forecasting future emission trends. This means we can make more accurate and sense-based assessments of how challenging it will be to meet the global temperature goals. Except for the government's level, at the society and the company levels, carbon trading markets also need timely data. Without up-to-date monitoring, it's hard to have a solid scientific basis for fair transactions. But a critical issue in the current field of carbon emissions is the traditional emission data are significantly delayed. As a result, actions and policies often rely on historical rather than timely data. So it's like a driver speeding on a highway, but only looking in the rearview mirror. If a deer suddenly jumps out, the driver cannot be able to brake in time. That's very dangerous driving for one person. And in the same way, relying only on the past data is dangerous for all the humanity when facing the climate crisis. Analyzing emissions with traditional statistics-based data is like reading yesterday's newspaper. You learn what happened, but only after the fact. And with the development of satellites, supercomputers, we can now collect and process information quickly. This gives us what we can call near real-time updates. Something like watching a live stream online where there is just a short delay. But the true real-time insight, like actually being inside in the stadium during the World Cup and seeing the action the moment it happens, is still not possible. We are limited by today's observing systems and computing power. And it is worth noting that there isn't a single definition of near real time because in different fields, this meaning can vary. But in the field of carbon emissions, traditional studies often had more than 1 year delay. And in our work, we work on reducing that delay to about only 1 month. So that's what we define as near real time in this context. And for the fossil CO2 emissions, I work on multiple sectors, like from transport, power plants, residential consumption, industry, and so on. And the current emission inventories include official inventories and the international institutions reports. The official inventories reported to the UNFCCC are annual, and only limited countries provide continuous inventories. For many other countries, the data are discontinuous across years, and some countries even do not provide official inventories at all. In addition, some international organizations contributed to publishing global inventories. They provide some inventory map data, but this so-called monthly data are simply based on the fixed monthly allocation factors, so they cannot reflect the real monthly variations. And also, these data sets usually have more than 1 year's time lag. And the main reason for this inventories, time lag, and cost resolution is that they rely on traditional statistical reports as activity data to calculate the inventories. And as we discussed earlier, such energy statistics have limitations in both resolution and timeliness. So the real breakthrough in this field comes from finding the suitable near real-time proxy data to take the place of the traditional statistics to improve the inventories. Recently, advancements in technologies such as multiple observation, like remote sensing, offer an opportunity for near real-time field. And beyond the timeliness for the temporal resolution, there are some studies that have tried to improve the monthly or daily estimates at the national level. But like for the EDGA, they rely on the fixed monthly allocation factors rather than the true monthly activity data. And there are some studies have improved the daily estimates at the national level, but they depend on the proxies that cannot be updated continuously. For example, they rely on lockdown levels during the COVID-19 period, or they use some single level proxy like mobility data to represent the emission changes across all sectors. So the real challenge, therefore, is how to identify and collect the suitable near real-time daily proxies with good quality for each sector. That is the key to building the more accurate and reliable high-frequency emission inventories. So we overcome the above challenge and established the carbon monitor to achieve near real-time monitoring of CO2 emissions. It improves the timeliness from a lag of more than 1 year to only 1 month delay, and improves the temporal resolution from the original annual change to daily resolution. Here is a video to show what we did. As you can see, previous inventories only provide annual emission data, and our data set for the first time provides daily emission tracking and has been updated in near real time since 2019. This allows us to capture clear seasonal pattern within each year, and it can also reveal the impact of some short-term events on emissions. For example, China's Spring Festival and the COVID-19. And for the detailed data and the methods we used, we use the improved IPCC bottom-up inventory accounting model. We employ near real-time human activity data to estimate emissions instead of the traditional energy statistics with high latency. By integrating sectoral human activity data for different sectors, such as the near real-time flight data for aviation sector, the temperature data for residential consumption sector, the TomTom traffic congestion index data for ground transportation sector, and some power generation for electricity sector, and so on. We calculated the near real-time daily sectoral CO2 emissions at the national level, called carbon monitor. Carbon monitor calculated the CO2 emissions in 7 sectors, including industry, power, residential consumption, ground transportation, domestic and international aviation, and international shipping. As you can see from this figure, for different sectors and for different countries or regions, we collected, filtered, and integrated a variety of data sources. This framework shows how our carbon monitor works. We rely on big data from multiple sources, including satellites, statistics, simulations, and so on. The real challenge is in data pre-processing. These data sets come in different formats, different temporal resolution, spatial resolution. We use customized crawlers, cloud-based pipelines, and supercomputing power to collect, clean, standardize, and integrate these multiple data sources. Only after this complex process, we can generate consistent near real-time proxy data, and then generate global near real-time carbon emission data set. And so far, the automation process has been completed, and this data set can now be updated continuously. And in order to improve the spatial resolution from national level to grid level, we use global spatial patterns from CO2 emissions to downscale the national totals to grid level. And for large countries via major emitters, we further employ a subnational proxy according to NO2 concentration retrieved from Chop-Almi to distribute national level total into subnational totals, and followed by a 0.1 degree downscaling according to the spatial patterns from EDGA. This figure shows the detailed method framework of the downscaling. It uses the spatial patterns from EDGA as well as a subnational proxy according to Chop-Almi NO2 retrievals in order to distribute the carbon monitor daily emissions at country level to the final grid. Next, I will introduce the results we got and share some key patterns and insights from them. We provided GRIST, the first near real-time global graded daily CO2 emissions dataset. It can be updated in near real time with a spatial resolution of 0.1 degree and a temporal resolution of 1 day. In addition, GRIST can focus on the provincial or even urban level, city level in space. So it can contribute to more effectively support the realization of local climate mitigation goals. And such timely and high-resolution dataset can reveal patterns that were previously not captured by traditional data sources. For example, we are all familiar with the seasonal variation of atmospheric CO2 concentration. It generally lower in summer and higher in winter. This is because plants absorb more CO2 during the growing season in summer. And the winter, it should be noted that the winter we are talking about here is the winter in the northern hemisphere, where most of the population lives. But what we didn't know before is that CO2 emissions from human activities themselves also have clear seasonal patterns. We can see that from this figure, emissions are typically higher in winter due to the heating demands, and also relatively high in summer due to the cooling needs. In contrast, spring and autumn have lower emissions. In addition to the seasonal pattern, we can also clearly observe the a sawtooth-like pattern in the data. This reflects the weekly fluctuations in human activity. Emissions are higher on weekdays due to work-related activities, but lower on weekends due to reduced activity. Here we show how daily data help us capture the impact of some short-term events, like the impact of COVID-19 on emissions. On this figure, you can see the global CO2 emissions in 2019 and 2020. There is a clear drop in early 2020. It is when the pandemic hit and many countries went into lockdown. And from this figure, you can see that 2020 recorded the largest decline in annual emissions in modern history. It is even bigger than during the oil crisis and the 2008 financial crisis. This highlights how unusual the pandemic was in changing human activity and the relevant emissions. And these sectoral plots tell us more. You can see that power, industry, transport, and aviation all dropped sharply in 2020 compared to 2019. And among these sectors, the transport and aviation show the biggest reductions. This is because the travel restrictions cut down mobility. And power and industry sector also fell, but not as much. While the residential consumption emissions actually almost unchanged. This is because people stayed at home more during the COVID-19 pandemic. Traditional datasets would not have shown this in time, but with our daily near real-time data, carbon monitor can make it possible to track these shifts as they happen. Global failure to achieve a green recovery. You may have asked yourself this question as well. After the sharp drop during COVID, did the world manage to keep emissions down, or did they rebound? As our figure shown, emissions actually rebounded very quickly. And you can see that in the first 9 months of 2022, global daily emissions averaged about 98 million tons of CO2. That's 3% higher than 2019 and almost 11% higher than 2020. So the answer for this question is clear. Instead of a green recovery, we saw emissions rebound above pre-pandemic levels. And with the near real-time data, we can also see the most recent changes in anthropogenic CO2 emissions. It allows us to timely evaluate the emission pathways. As this figure shown, although global CO2 emissions dropped sharply in 2020, they rebounded significantly in 2021. And based on the current data estimates from our data set, global emissions are still going up. This increasing trend doesn't match the emission pathways needed to keep warming within 1.5 degree or even 2 degree. The IPCC says global emissions should peak before 2025, but this is not what our data are showing. In light of these recent changes, we have also updated the estimates of the remaining global carbon budget under the Paris Agreement temperature goals. We see that if the current emission levels continue, the world could exhaust the entire remaining carbon budget within the next decade. Therefore, urgent action on climate mitigation is very necessary than ever. On the previous slides, we looked at the daily and monthly changes, but near real-time data can go even further. Here we show hourly data on power generation for different countries and regions. These curves clearly reflect the daily cycle of energy production. For example, power generation is usually lower at night, then rises in the morning as demand picks up, and the generation peaks during the day. In the evening, generation often drops again. What's important here is that this hourly data allow us to see the fine details of human activity and energy use. This data captures the short-term patterns that annual or even monthly data can usually miss. This kind of high-frequency monitoring helps us better understand how energy systems actually operate in real life. It gives us valuable information for managing grids and planning for low-carbon transitions. This data set emphasizes near real-time capability. Its update frequency and release speed are higher than those of other databases. But a critical question here is how to verify the accuracy of this data set. For grid level, uncertainty analysis of grid gives a grid level to sigma uncertainty value of 19.9% generally, which can be acceptable compared with the uncertainties of the similar grid datasets. This indicates the reliability of grid was not sacrificed for the sake of higher spatial temporal resolution. And the comparison with other similar datasets also shows the similarity in emission distribution and the number of non-zero emission grids among them. It represents grid has been verified by other similar datasets to some extent. In addition to the grid level at the global level, we also compared our data with other databases. This figure shows a comparison with other annual inventory results. As this figure shown, our data aligns well with those like from IEA, from JCP, and this figure shows the comparison with other daily researches. They also align well. However, such other daily resolution databases have not been updated for a long time, so we compare it for the limited time series. In summary, we used the improved bottom-up inventory model to achieve the near real-time monitoring of CO2 emissions. Well, situation is very different for fossil methane emissions because bottom-up inventory model cannot account for the abnormal methane links. Well, this part of emissions cannot be ignored for quantifying the complete fossil methane emissions. So I use top-down inversion model method here to achieve the near real-time monitoring of fossil methane emissions. In summary, one big challenge of higher temporal resolution is that it will bring a lot of uncertainty. And my work addresses this by first building a near real-time monthly methane inventory, which can provide stable and dynamic prior information for inversion model. Another challenge is timeliness. The inversion process is computationally intensive and depends on other data sets like OH, like prior inventories, which can usually not updated timely. To solve this, I developed near real-time inventory, and my collaborators produced near real-time OH data. So together, these efforts make near real-time methane inversion possible. In addition, there is an underestimation problem also exists here. If we just rely on a single observation data or simple data fusion of multiple observations, that will lead to monitoring gaps due to the limitations of satellite technology. So my model integrates different observation sources for different spatial scales, not just a simple data fusion work. ChopOmi offers higher sensitivity for local monitoring, while GoSat satellite can provide stable observation for global coverage. So my model uses GoSat and ground level network as a space, and with local improvements from ChopOmi satellite for global 13 major basins and thousands of point source ultra emitters. This data fusion approach helps capture the underestimated basin emissions and the missing methane linkage that the national reporting inventories miss. This is the method framework of my study. I integrate global inversion data based on the observations from GoSat and surface networks with 8 days temporal resolution, with a downscaling work from a 1 degree spatial resolution to a final 0.1 degree resolution based on the emission activity maps. And it is further enhanced with daily and monthly ChopOmi inversion data for ultra emitters and the K basins in the world. And for the results, the inclusion of troponin-based inversions for ultra emitters accounts for emissions emitted from inventories. And we can say that, like for the coal sector, since 2021, India has surpassed China to be the top ultra emitter for the coal linkage. And in the oil gas sector, we can say that Turkmenistan experienced a sharp rise in 2022, driving a global rebound in methane linkage from oil gas sector. And our emission estimates can also show that there is an underestimation problem from the UNFCCC inventories. The majority differences between our estimate and the official reports are from oil gas sector. And it is shown that the top 3 countries with the most significant underestimation are Turkmenistan, the US, and Russia. And in the coal sector, emissions reported by official inventories are higher than our estimate. The difference is mainly from China. This might be explained by the emission factors used in the UNFCCC that may be overestimated for China. Yeah, and in terms of the data availability, we established visualization and download the website. Here are a few videos. The highlight of this website is that you can see changes over time with a timeline at the bottom. And furthermore, you can also filter the date, the sector, and the area you are interested in for display. We hope by establishing such a website can support researchers, institutions, or governments in need. And for methane emissions, we also published the fossil inversion results on this website. And you can see the spatial distribution for different sectors. Yeah. So in summary, Carbon Monitor project is contributed by more than 30 international research institutions. We developed and published series of databases at different levels. And all of them can be downloaded. And you can see there is grade level and national level. And even for some countries like China, US, we provide provincial level or state level. And we also selected thousands of major cities to show their CO2 emissions. This data set has been downloaded over 1 million times and has been recognized as the highest international levels. For example, it was cited as the national report presented at the United Nations SDG Summit. And it has also been used by the IPCC, the Global Carbon Budget, as foundational data. And it was highlighted in a keynote speech at COP28. And there are some relevant publications around our Carbon Monitor project. I think this research holds exciting potential for the future. The first one is such near real-time data on energy-related carbon emissions can reflect how people use energy. For example, analyzing the near real-time data for California will help us understand when, where, and how people consume energy. I think this information can guide adjustments to the use of.
Xinyu, so sorry to interrupt. We'd appreciate if we can start discussion in like 2 minutes, and we can go back to this page to discuss more exciting future directions. Yeah.
Okay.
Yeah.
Okay. So yeah. So I think I move to the takeaway. Let me close with some takeaway messages. First, different greenhouse gases emissions need different quantification methods. Like for CO2, the carbon satellite technology is not yet mature, so we rely on optimized bottom-up inventories to achieve the near real-time emission estimates. But for methane, things are different. Because of the ultra emitters linkage, inventories are not enough. That's why we use top-down inversions, combining multiple satellite observations to monitor the near real-time methane emissions. And second, the data set we provide is near real-time and high resolution. It can capture the short-term events like holidays, lockdowns, or extreme climate events that traditional miss, and can provide sectoral and subnational insights. Third one, this data set has broad applications. For example, in science, it can provide near real-time constraints for atmospheric models and help us understand emission dynamics at daily to seasonal scales. And in policy, it gives timely information to track Paris targets, improve transparency, and even support carbon markets. And yeah, and in addition, in society and engineering, it shows how energy systems, transport, and even cities behave in near real time. So researchers in relevant fields can use such near real-time carbon emissions data to study the systems they care about. So no matter your background, science, policy, or society, this data set offers valuable insights and a chance for collaboration. That's all for my sharing today. Thank you very much for your attention, and I'm open to questions and discussion.
Thank you very much, Xinyu. And Scott, I'll let you to moderate the discussion.
Great. We have a few minutes for questions. By the way, my name is Professor Scott Moore at the University of California, Berkeley. Dr. Dou, fantastic and very inspiring presentation. So for those that are with us here on Zoom, now it's your turn. What questions do you have for Dr. Dou? Feel welcome to raise your hand, or you can unmute and ask away.
Yeah, you can unmute yourself directly if you have question. Yeah. Maybe start from some clarification question. Do you want to Dr. Dou to help you review some concepts, ideas, key methods? Yeah, feel free to ask.
Hi, Dr. Dou.
Hi.
Thank you for an excellent talk. I do have a question about like the data fusion work. So I'm wondering if you have you ever met like a problem like when we try to incorporate multi-source data, we may observe some discrepancies between different data sources. So if we do met that problem, how do you handle this?
Yeah, like for as a first step, we collect, filter, and decide the most suitable data source for like each sector or for each country. So we filtered the data sets at first by the timeliness of data, the resolution of data, and evaluate this data source accuracy. So I think this can avoid such problem. What we face with during data processing is that, like, for some data sources, maybe they cannot provide the resolution we expect, or they have some data gap. So we need to do some standardization work, and to use like some machine learning and model to fill the data gap, so that we can standardize all data sources to a consistent format to the resolution we expect.
Okay, I see. Thank you.
Thank you.
Okay, good question, Jiaqiao. Give us another one.
Maybe I can ask a follow-up question. So currently in the framework, your team crawl and collect all these data from all different sectors. But I think there are also some domain knowledge of different sectors, like the emission data in power sector may different from the way to collect those data may different from the way you collect those emission data in the mobility sector. So we have audience from all disciplines, from all application fields. My question is, which sector do you think it's in most urgent need for improvement, and what's kind of the way or what kind of data you want to improve the quality of emission data from some specific sectors? And I think maybe in our audience there are some people who are very willing to help you to further improve the quality of the data set.
Thank you. Yeah, on my side, I think the industry sector needed to be further improved, because like we in the future plan, we expect more local data, like for the infrastructure level of industry, the locations, the area, and the specific activity data at the infrastructure level. So I think I'm very excited to see the opportunity to have some cooperation from with the researchers from this field. And what we think is the most is the data set, the sector with the best good quality is power sector. Like for the power sector, we can also provide not even daily resolution, but also hourly resolution data. And you can see the energy structure of the power generation, so that it can contribute to the energy transition, the use of more renewable energy. Yeah.
Great. I think we have one more question from Professor Marta Gonzalez. Please.
Hi, Professor Dou. Thank you so much for a beautiful and very relevant research. I'm glad that you are talking to us that come from the more high resolution activity type of models. I would like to pick your brain on the opportunities regarding the emissions due to individual drivers. In California, we're measuring a lot the car kilometers traveled per capita, and we know there are three variables: congestion or traffic, car efficiency, and the actual vehicle's kilometers traveled. So how much each car, you have an efficient car or an inefficient car, but how much is the kilometers traveled? And I noticed in your data set for transportation, you use the very useful TomTom traffic index. That doesn't give you cars kilometers travel or vehicles miles travel. Do you have some initiative in which we can connect the type of work you do with these three variables? Again, I know you mentioned freight transportation, but I'm very interested in the private vehicles emissions, which is the majority of the transportation emissions in the US.
Yeah, thank you for your question. Yeah, for the first question, now for the ground transportation sector, we use the top-down contraction index as our activity data for this sector. And actually, we use a fixed emission factor and use the top-down index to capture the activity changes compared to our baseline activity level. So now in our current study, our emission factor is from the baseline year, but we expect that if we can improve the emission factor for different years and for different regions by using some local monitoring data, maybe from your work.
Car fleet type of cars is one aspect, and the distance travel is and it's not too hard to find distance travel.
Yeah, you mean the distance, right?
Yeah, because it's which cars are traveling and for how much they are traveling. And of course, it correlates with congestion, but it matters a lot, this CO2 footprint from the rural areas. They tend to produce more.
Yeah, it's very important to integrate these variables in our future research. And for our current research, we use congestion data as the activity data for this sector. So I think in our future work we can improve the emission factor, varying by time, varying by regions.
Thank you.
Yeah. And for the aviation sector, now our flight data is collected from a private company. It's from our collaborator of Carbon Monitor project. Yeah.
Okay, thank you. So time is up. So let me first announce our next speaker. Then we will stop live stream on Zoom, recording on Zoom and live stream on YouTube. But people in this room, you are fortunate. Dr. Dou agrees to stay longer to answer any of your questions. So I see some other hands. We will stay here to discuss further questions. Next Monday, 4 p.m. This time we will be in person, but still there will be Zoom and YouTube options. We are fortunate to have Dr. Jacqueline Dou, who is currently also a Stanford Energy Postdoctoral Fellow, but she succeeded in the job market past year, and she will be an incoming assistant professor at University of Iowa. So I think it's very unique to have a combined perspective, mixed perspective as a student and also as an incoming assistant professor. Her talk will be on weather constraints, how weather constraints will guide optimization of energy storage systems and heat pumps. Meanwhile, we still have some open slots, so feel free to suggest someone you know or suggest yourself to be our next emerged speakers.